So we are going to look at correlation of multiplicative functions. So what do I mean by correlation? So first of all, I would start with multiplicative functions over integers. So all our functions are going to take value in the unit disk. Otherwise, things become a bit complicated. Some of the things will not work. So this is the unit disk. And by correlation, I mean this is some like this. So f of n, f of say n plus 1, just a shifted argument, and then n sums up to x, and you are going to take a look at the average. So we would do this. So with this general setup, you can ask many questions for this correlation. For example, you can ask if it when does it go to 0, and when doesn't it go to 0, and if it goes to 0, you can talk about the rate of decay, and if it doesn't go to 0, then you can ask for the mean, what you get be the mean. So of course the one of the central theme is the big conjecture, this Chawla's conjecture. So I'll write it down. So this is one of the version of Chawla's conjecture is the following. So your multiplicative function is the Liouville's function. So lambda n plus, you can actually ask for any fixed d. I mean, you don't have to always put 1, you can just change it to any fixed d. So d is fixed positive integer. And then n less than equal to x. And you are saying that this is little o of log x, so little o of x. So what I mean is that if I divide it by x, then it goes to 0 as x goes to infinity. So there are several versions of Chawla's conjecture and generalizations. So I would usually refer to this kind of thing as Chawla-Elliott conjecture, because there were some generalized versions by Elliott. And so this is still open, it's not known, but what is known is a logarithmic version. So this is Terence tau. So this is what is known as logarithmic Chawla's. Okay, so just to keep it self-contained, so I will also define what this function is. So this is minus 1 power the number of prime factors of n counted with multiplicity. So which is written usually as omega of n. So that's what is the Liouville's function. So Tau's version of this theorem is there is a normalization by an n, and then of course the question slightly changes. So this is little o of log x. So of course this is going to imply this, but this does not imply that. And So, and this is known as logarithmic Chawla because you are putting this 1 over n, and it is little of log x because the summation 1 over n, the sum of the reciprocals up to x is about log x. So that's the correct thing to do. Little o meaning this divided by log x will go to 0. But Tau's theorem is not just this, it's much more general actually. So that is where I want to go. So what he proved actually, this Tau's theorem is much more general. So I just emphasize that this is really quite general. So to get to this, so when should I stop? 4. Yeah. Yeah. No. I've learned. I mean, I'll probably finish in half an hour. So anyway, yeah, so much more general version. So to get to the general version, let's just start with this question that the more fundamental question that when does such a thing go to 0? When is the correlation 0? When does this function 1 over x or in other words we are asking for what kind of function say if this goes to 0. So when does this go to 0? So what are the kind of functions such that this happens? So what are the counter examples where it does not happen? So one of the thing is if fn is a Dirichlet character, then it doesn't go to 0, and it's in fact slightly more generally you can take a Dirichlet character and put a n to the it for a real number t, for a fixed real number t. So for these kind of things, so correlation doesn't go to 0. So I would write positive correlation. So they have positive correlation, doesn't go to 0. And now what Tau proved is that if a function is not close to this, then this correlation goes to 0.
There is some correlation between t and character, the character of the character.
T no.
No, the end will like t.
Yeah, anything will do. Yeah, that mean would involve t and the conductor, of course. Yeah. So these functions have, so essentially Tau's result says that these are the only exceptions in some way, in some sense. So what this result says that if f is away from these kind of functions, that Dirichlet character multiplied by n to the it, then so I would explain what this word I is. I mean that's the crux of the matter actually. So if f is away from these kind of functions, then then to use the usual language, so people say that this is an autocorrelation because we are looking at the same function. So it is, then the autocorrelation is small. Autocorrelation Okay, let's write autocorrelation is 0, goes to 0. And then what is this this adjective away? So that brings us to the distance between multiplicative functions, which is now known as Granville-Soundarajan distance. Granville-Soundarajan distance. So between two multiplicative functions, so this is defined as d of f and g are multiplicative functions, and x is some quantity usually large. This is defined by the summation. So all functions whatever I talk about all takes value in the unit circle. So otherwise this will not make sense what I am going to write now. So this is 1 minus real part of a p is prime. So these functions are evaluated at prime, gp bar divided by p.
You mean less than equal to 1 S1 or inside a disk?
Inside the disk. Yeah, yeah, yeah. It can take 1 as well. 1 is okay.
No, they're doing chi as well. You take zeros.
Yeah, no, not inside the disk. Yeah, disk. Yeah, so this is the distance. Actually, this quantity is not written down by Granville and Soundarajan for the first time. This thing is around since Edos, but the interesting thing was what Granville Soundarajan wrote down is a triangle inequality for this. So this actually behaves like a metric, though it's not a metric. Of course, it's not a metric, but it is. It has a triangle inequality which is very useful. Yeah. Okay. Yes. Yeah. So now we can state what Terence-Tau proved. So Tau's result. So what I'm the same thing that I'm talking about in. So now that the exact result is like this, it's much more general, as I said. So this is. It says infimum. So if infimum of real numbers less than equal to x. So distance between f and chi n to the it. So this distance, so because we don't have a nice notation for this, so I am just writing down the full function. So what I mean is that distance between f and this function that I was mentioning. So if this distance and then also vary the t. So t is a real number between minus x and x, and take the infimum. So we want this infimum to go to infinity. So this diverges. So the distance keeps increasing. So they are not close. So if this goes to infinity, then you have the result. It's a little O of log x. Okay. So and if this kind of thing happens, that the distance is going to infinity, then we say that f does not pretend like this. So in other words, we say that f is non-pretentious. So you can just summarize this in one line just in language, that non-pretentiousness So non-pretentious implies, or non-pretentiousness you can say, it implies small autocorrelation. So if a multiplicative function does not pretend like or very close to, you can use both the language, it's the same thing. If a multiplicative function does not pretend like this, a Dirichlet character multiplied by this into the IT, then the autocorrelation is small. In other words, in concrete terms, this thing goes to 0.
So what you're saying is that the obvious obstruction to the first problem,
Yeah.
you get the function distant from there,
Yes.
solve the second problem.
Yes, yeah. Exactly that.
Is it clear if I take f is equals to the Liouville function, this goes to infinity?
Yeah. No, probably not very clear. No, this little bit of, some little bit of work is to be done, yeah. Okay, so what?
Also, you have to check it for every kind of distribution.
Yeah.
You have to check for
Yeah. So unless you have a general method of checking, yeah, right. Yeah, I mean you cannot just take every conductor and check it. But yeah. Okay. So the idea of my talk is to explore this phenomena for multiplicative functions on function fields. So multiplicative functions on polynomials over finite fields. So I'll just come to that setup. So everything will remain very much the same, only the domain of the function changes. So now the multiplicative functions are okay. So let us start like this. So we have the finite field of Q elements, and then look at the polynomials. So this is the polynomial ring, and this M, the script M, is going to denote the monic polynomials. So monic polynomials would just behave like integers. They would do whatever we know for integers. It is just a analog for integers, and the irreducible polynomials would replace primes. Irreducible monic. Irreducible monic would replace prime. And then we can again go to the same kind of question. So multiplicative function would be exactly defined in a similar way. So I'll start with M. So these are now integers for us. And then ask the same question. So let's first write the average. So the correlation would be a sum like this. So what we want to do, we want to sum over. So okay, actually I would use the notation phi, psi, etc. for functions there, because I would require f, g, a, b for the capital letters for usual capital letters for the polynomials. Yeah. So now I write the correlation. So psi of, say, f, psi of f plus some h, some fixed h, and then I am going to sum over the monic polynomials of degree n. So that also is a notation to be written. So this is monic of degree n. Exactly n. Yeah. Sorry?
Definitely m plus h.
Yeah, h I would generally take to be of smaller degree. Yeah, so h is generally a small degree. And yeah, so. And then I have to divide by the number of polynomials, so which is q to the n. Number of monic polynomials with fq coefficients. So divide by this. So that will be the correct that will be the correct analog. So now there were two things, two parameters come in where we can look at the limit. So the first thing is n goes to infinity with q fixed, or we can look at q goes to infinity. So they actually offer very different pictures, very different methods as well. So this is generally called the large degree limit, and large field limit. Yeah. Okay. So I will not be able to sort of comprehensively survey the result, but I'll just mention some. Yeah. So what is known about Chawla now? So in this situation, so I'll call Chawla Elliott. So all general versions. So I'm not stating the theorem. Liouville's function is going to be defined in exactly same way. So very analogous way. So just because you have analog for everything, for primes, prime factors, everything you have analog. So you can define in the same way. So this is. So now we have two situations. One is this large degree limit, large finite field limit, and yeah. So let me just say that properly. Yeah. So large finite field limits. So large finite field limit, it is known. So this is Carmen Rudnick. And a large degree limit. So I would write Chawla for lambda for Liouville function. So large degree limit, this is Savin-Susterman. So both are known. So in both these cases, the Chawla conjecture is known. But these proofs are not pretentious proofs, so to say. They do not work in generality. So it's not an analog of Tau's result. So Tau's analog of Chaw's result, this Chawla Elliott, this logarithmic Chawla Elliott is also known. So this is due to. So these two are not pretentious. This one is pretentious proof. So it works in exactly similar kind of generality. So logarithmic Chawla. Okay, I'll just write logarithmic version. So this is pretentious approach. So that's it. That's an exact number. Yeah. Sorry.
What is the logarithm version?
Yeah. Okay. Logarithmic version is just this.
Yeah, so there it was 10.
Yeah.
Now it's catch. So catch was different catch.
Yeah. So okay. So logarithmic version is just this. So shao of p. Yeah. Exactly. So that should be written actually. Yeah, see it's so the dividing by n is not obvious. So, so this is actually divided by q to the degree of, sorry, one second.
So if moving is less than equal to 35 to the degree.
Sorry?
If moving is m is moving degree is less than equal to n,
Yeah.
then you get.
Yeah. So then I can yeah, right. Yeah. So yeah. So that is this is monic of degree f is less than equal to n. Yeah. It's less than equal to n, and then you are dividing by the q to the degree n. So that is again n. Yeah, q to the degree n. Yeah. Q to the degree n. Oh, sorry, q to the degree f. Yeah.
You are taking the absolute value here. You have the mod n, you just is a degree variation.
Yeah. Yeah, so then this is little o of n. That should be the replacement for log. Yeah, so this logarithmic Chawla-Elliott is proved by Klurman, Mangrel, and Teravainen. I don't know how to pronounce their names actually. So these three authors, Klurman, Mangerel, and Teravainen, they have proved this logarithmic version in pretentious approach. So it has a result like that if the function is away from the natural obstructions, then this is true. This is in n aspect. Yes. This is in n aspect. So this is So this is large degree. Yeah. So this result in the q aspect is not known. Yeah. I mean, this you cannot ask that naturally here, but here it is a natural question. Okay. Okay. So I put. Yeah. Let's erase this part. Okay. Yeah. So now for the next last 10 minutes, I want to come to the things that I am doing, which is the other world. So it is the non-pretentious world. So that's the pretentious world. So if a function pretends like something, meaning this natural obstructions. Actually, I have to talk about what the natural obstruction here in this function field. So, okay, maybe I should just talk a little bit about that and then come to this, because otherwise it will not make sense. 1 second. Yeah, so there is something to be observed. There we had the Dirichlet character. So, Dirichlet characters essentially is a detector for arithmetic progression, but here the situation is different, because if you take, so in very simple case, so if you take two polynomials f and g which are monic of degree n, and then with the condition that f and g are congruent mod say a single power x to the L, just x to the L, then what does that mean? So, you are defining it in analogous way. So, the difference of these two polynomial is divisible by this x to the L, and so you can write it as ax, another polynomial, another monic polynomial x to the L, and therefore and this polynomial has only terms which has degree more than L. So, it is at least the least degree is L here. So, therefore, all the terms which has degree less than L are the same for these two polynomials. So, all the terms which are less than degree less than L, they agree for these two polynomials. So, that's a extra feature that comes from this congruence, and this is what is captured by what is called Hayes character. So, Dirichlet characters will be replaced by some other character with very similar construction. I really do not have time to talk about that. So, these are Hayes characters. So, it was used by David Hayes for the first time, so it is called Hayes characters. So, these are going to replace our Dirichlet character. Now, at least as far as this pretentiousness goes. Okay, let me just come to the pretentious world. Pretentious world in this polynomial setup. Okay. Just skip to the last part actually. Yeah. Yeah, so now for the pretentious world, so I'll define this two kinds of correlation. So, let me just introduce this notation S2. So, I have 2 point correlation. So, in Q, so this is what what I wrote previously. So, this is the same thing. F in Mn, this is my multiplicative function. So, it's I of f plus h. And then I define some local factors. So, local factors of this function, so which are defined local factors of these multiplicative functions. So, they are defined in this way. So, for a prime, meaning irreducible polynomials here, so this phi of p f is defined in this way. So, this is phi of p to the m if p to the m exactly divides f, and 1 if p does not divide f. So, that is the local factor. And local correlation is the following. So local correlation at a prime p, so an irreducible polynomial. So I am just writing it as v of p. This is already a limit, n tends to infinity 1 over q to the n. So it's exactly the correlation of the local functions, but I have already taken the limit. So correlation of the local factors. Yeah. I'll erase this. 5 minutes. Yeah. Yeah, so this is local correlation. So to put it in a nicer language, I can call it global correlation. And then relate them. So if the multiplicative function pretends to be so the definition of pretentious is just the same. So the distance goes to, I'll write actually. So it pretends to be, I'll write it down, pretends to be 1. So what do I mean? So let me just write that. So I am adding over all irreducible polynomial, and this is 1 minus real part of psi of p divided by q to the degree of p. So this converges. So this is just psi of p into 1. So you can think of psi of p into 1. So I am saying if this happens, then I am so this is what I mean when I say that psi pretends to be 1. So if this series converges, and if that happens, then we have a local global theorem. So then S2NQ converges to the Euler product V. So this product as n goes to infinity. So here for local correlations I have already taken the limit. So this only depends on p. So and then these products. Yeah. Okay. So this is a joint work with Pranendu Dorbar. And so this has a nice application. So the application is this. So okay. So now this slight difference. So psi from the monic polynomials to S1. Now I am taking S1. So absolute value 1. So S1 and completely multiplicative function, not just multiplicative, completely multiplicative. Completely multiplicative. So if it is completely multiplicative, satisfying the following, that if you look at the difference of psi of f to psi of f plus say 1, so I mean just anything will do, anything fixed, I am just writing 1, and then f sum over the monic polynomials of degree n. So if this is little o of qn, then this function is actually of this form. So this is an Hess character. So you can so this is, as I said, they are replacements of Dirichlet characters. So this actually has a Dirichlet part plus another part which is called small interval, short interval character. So that's what is the Hess character. So some analog of Dirichlet character for function fields. This into and this n to the it. So n to the it is now replaced by e to the some I theta. So if I write it like f, then I should say, okay, let's write it with an f. So a polynomial. So this is e to the some kind of angle actually. So just degree of f. So for some theta between 0 and 1. So this condition actually gives us this this characterization of such functions. If this is satisfied, then this. In number field setup, this is known as Katai's conjecture. That has been proved. In function field also, this is proved in various ways. So we proved it in this pretentious approach using this local global. And how I just write one line. So how does this relates to this, the correlation? So that is nice. So it's actually a very trivial inequality. So if so this psi of f plus 1 is equal to 1 minus half So this completely trivial inequality is so completely trivial equality relates this condition to correlations. So we can use correlation estimate to get this. Yeah. So okay, I'll stop here. Thank you. Which product? No, if they are pretends to be 1, no. So
the product of APs would be non-zero.
yeah, that will be non-zero. Yeah, that will be non-zero. In general, because of this pretentious condition, it's going to be non-zero. Yeah.
So that's the analog of Saundarajan distance function.
Yeah. So this is the analog of Saundarajan Granville distance.
Or half. You don't need that.
No. I mean, we need that. No. That is also all these definitions remains exactly the same. But here, just the convergence is enough. So here it is, you are taking all primes, not up to some degree, but everything.
So instead of g function, you are taking g to be 1.
G to be 1, I mean that is what pretends to be 1. Actually, when you are looking at this this situation, that when something pretends to be, so you don't really need to take this full thing. It's enough to take 1, because you can always kind of adjust. You can just divide by you can just modify the original function by this and then say that it pretends to be 1. So, yeah. So it's good enough to just look at 1.
Very good. So let's thank